Okay, welcome to checkpoint 2 for further mechanics, the second part of momentum. Here's our first question. So we've got a girl kicking a ball along the ground at wall 2 meters away. So we've got somebody kicking a ball 2 meters away from the wall. The ball strikes the wall normally. This just means it's at right angles to the wall at a velocity of 8 meters per second. So it's going to go this way at 8 meters per second. And it rebounds in the opposite direction with an initial velocity of 6 meters per second. So it's coming back 6 meters per second. The girl who has not moved stops the ball, so she traps the ball nicely there. Explain why the final displacement of the ball is not 4 meters. Okay, so the important thing here is the ball's travelled 2 meters that way and 2 meters back, but displacement is the distance travelled from the origin, and the distance travelled from the origin is 0. Okay, so the kind of answer you're looking for here is something to say that displacement is a vector. This is the crucial word, quantity. Okay, so it's moved, if you like, plus 2 meters and minus 2 meters, but it's ended up back where it started from. Explain why the average velocity of the ball is different from its average speed. Well, again, it's travelled at 8 meters a second and 6 meters per second. We could work out an average speed. You'd have to be careful. It's not 7 because it spent more time travelling at 6 meters a second than it did travelling at 8 meters per second. But you do some sort of calculation like that to get an average speed. But the average velocity, well, velocity is the change in displacement with time. And we've just said that the displacement is 0. So again, because the displacement is 0, therefore, the average velocity equals 0. I probably should have put average velocity equals 0 meters per second in there. Okay, again, because it's a vector quantity. Okay, to get some numerical questions, so calculate the average acceleration of the ball. Well, the ball has hit the wall for 0.1 seconds, so remember it was going that way at 8 meters per second, then it was coming this way at 6 meters per second. The average acceleration of the ball, well, for acceleration we're looking for the change in velocity divided by the change in time. Crucially, the change in velocity is 14 because it was going at 8 meters per second to the right, let's say, and 6 meters per second to the left. So this is 14 over 0.1, which is 140 meters per second squared. Calculate the average force acting on the ball. Well, we know one way to do this at least is F equals ma. So all we've got to do is the mass, which it gave us in the question here, so 0.45 times 140, and that comes to 63 newtons. If you take in this way as positive, you might want to put minus 63 newtons because on both of these, because the acceleration is to the left, but we've not really specified, so that's okay. You could, of course, do that the force times the time is the change in momentum, and the change in momentum is from 0.45 times 8 to 0.45 times minus 6. Okay, so that would be another way of doing it, and then so divide that by the delta t, but that would still give you the same answer. So either of those methods is fine. State the direction of the average force. Well, it's, if we've drawn it this way, it's to the left, but obviously they haven't specified in the question which is left and right. So I would just say away. I would just say away from the wall, and to be really precise, at right angles to the wall, just to be safe there. Okay. It is 2 marks on the mark scheme, that. So you do really need to specify not just any direction away from the wall, but at right angles. Okay, so 2 quantities that are conserved in an elastic collision. Okay, so important that you're clear on this. Quantity 1 that's always conserved is momentum, but because it's in an elastic collision, then kinetic energy, and again be very careful to use the expression kinetic energy. Okay, again, all energy is always conserved. So we've got a gas molecule which makes an elastic collision. You'll do some more about this when you do about gas laws later on in year 13. With the walls of a gas cylinder, the molecule is travelling at 450 metres per second at right angles to the wall. What is the magnitude and direction of its velocity after the collision? Well, the point about it being an elastic collision is it must have the same kinetic energy afterwards as before. Okay, so it must be 450 metres per second away from the wall. Okay, and again, we probably should say something along the lines of normal to the wall, because it was normal to the wall on the way in. Calculate the change in momentum of the molecule during this collision if it has a mass of 8 times 10 to the minus 26 kilograms. So again, we've just got to be careful. It was going 450 metres per second in that direction before, afterwards 450 metres per second in the opposite direction. So the change in momentum is the mass, which is 8.0 times 10 to the minus 26 kilograms, times 900, because it's gone from 450 to the right to 450 to the left. That comes to 7.2 times 10 to the minus 23. I like to use Newton seconds for momentum. Some people will do kilogram meters per second. So if you write that, especially if you put a K in the kilograms, okay, that is fine as an alternative unit. Okay, use Newton's laws of motion to explain how the molecules of a gas exert a pressure on the container, a force on the container. So the crucial things to understand here is that each molecule exerts a force as it collides. So this is, although you don't feel individual collisions, the total effect is the sum of all of the little collisions. So it's got a change in momentum. So in order for it to change its momentum, there must be a force on it. Sorry about the writing here. Molecule by Newton's second law. But then, of course, if there's a force of the wall on the molecule, then there must be an equal and opposite force of the molecule on the wall. So by Newton's third law, if the wall pushes the molecule, then the molecule pushes the wall in the opposite direction. Okay, just 3 quick multiple choice questions to sort us out here. So impulse, well, remember impulse is change, go back. Impulse is change in momentum. Force, hopefully we know force is a vector quantity, so we're just looking at this question, are these things scalar or vector? If we don't know force is a vector, we're in trouble, so it's definitely not this one, it's definitely not this one. Impulse is to do with momentum, so that's also a vector quantity, so it's not that one. So our answer to that one is D. Question 4, this is a force time graph. They do like to do these force time graphs. Shown is applied to a body initially at rest. So initially at rest is crucial because we're trying to work out its change momentum on a smooth surface. What is the momentum of the body after 5 seconds? So we know its momentum at the start is 0 because it's not moving. So to work out the momentum at the end, we just need to know the change of momentum. Well, the change of momentum is the area under this graph. Right, if you like, just to be safe, that's 2 triangles. So each one of those triangles is a half times the base, which is 2.5 times the height, which is 10. Okay, so that comes to 25 Newton seconds. So that's C. And then finally, the rate of change of momentum of a body falling freely under gravity is equal to its. Okay, so this is the rate of change of momentum. Remember the equation for this, right? Force times time is change in momentum. So the rate of change of momentum is F equals delta mv over t, or delta t if you like. So this is the rate of change of momentum. So that's just the force. Well, the force on it is its weight.